Hello everyone. I'm Richal here, and today my teammates Khushi, Savri, and Aditi would be joining me to talk on the topic Martian paraterraforming. So, let's get started. So, of course, we are here at Mars Convention, and still we ask this question, why Mars? So, we know that the next step of our space exploration is going to be Moon and Mars, and Mars is the closest planet that is to Earth, and also it is bigger than Moon, so almost as comparable to the size of the Earth. It also lies in the Goldilocks zone, and there are hopes for future human settlements with advancements in technologies and ISRU activities. So that's why we are having hopes from Mars. Next slide, please. So for motivation for settlement, so why do we desire to make settlements on Mars? So the first thing that comes to our mind is the human desire to explore new worlds, and also, of course, human wishes to make settlements on other planets to make sure the existence of the our very living beings, because we know in the past there have been certain events that has led to mass extinction of the species, and we want to make sure that in future we would like to avoid certain kind of deadly disasters. So that's another possible explanation why would we have settlements on other planets. And last but not the least, human settlements on other planets would be key to contribute a true planetary future. So that's why we would like to settle on Mars. So today we will be talking a bit about terraforming and its types. So terraforming is a concept wherein we convert the dead planet, as in a lifeless planet, into the land that could support different types of life forms or living organisms. So the idea is not just to convert the environment of this climate of this planet, but rather it should be able to encourage the flourishment of the life on its surface. So this process of converting the planet into a living planet just like that of Earth is very difficult, and especially when we are going to do it by artificial means. So that's why we have come up with a concept called paraterraforming. It's a concept wherein we will be converting some patches of the Martian surface into the green lands in under controlled volumes. So today we'll be exploring more about what is paraterraforming. So here we are looking at the artist rendition of how the paraterraforming world domes would look like. We also call them as world houses. So as I mentioned earlier, it's very difficult to turn the entire land into the land that could support life, that could have atmosphere just like that of Earth. So that's why we will be doing certain experiments, and we will be trying out with the different ecosystems that we could grow inside the world domes. And we would be starting this with some smaller greenhouses as an experiment, and then going to later stages of having some world domes at different locations on Martian surface. Next slide, please. So the methodology or the kind of thinking that goes into is this is like we will be dividing this large scale project into different phases. So of course the first phase is to land on Mars, and that as soon as we land on Mars, we will be starting with the construction of world houses with a few crew members at the beginning of this stage. And then after the construction of, say, small greenhouses or polyhouses, we will start building the environment control and life support systems. Once we see and we decide upon the locations, again we'll go back to the construction of global world houses, and then prepare the conditions inside such that it can support living organisms like plants and different kinds of trees, or maybe even algae or grasslands. And along simultaneously, it's very important to power these world houses, because our aim is to make this world houses autonomous with the minimum help of human support. So that's why we will be needing power generation and energy storage units. So, side by side, we will also be doing in situ resource utilization to tap as many resources as we could on Martian surface, to tap the resources and use it for making these ecosystems inside the domes. And once the domes are set up, once we are ready to go, we'll be conducting different kinds of experiments to see which crops or which plants and trees could be supported in such harsh conditions under controlled volumes. Once we get an idea, we will start multiplying this number of trees, crops, plants, and the job of, and also at the same time, we will try to convert these domes into full autonomy, wherein there is almost no human intervention. And then these rovers, robots, and drones would be working in swarms and will be looking at the maintenance activity. And then that's how we will go to the first human crew settlement stage. So in the upcoming slides, my teammates will be diving more into the details of all these phases. So over to you, Khushi, over to you, Aditi. Yeah.
Yeah, thanks, Richal. So I'll be taking this presentation further and talking about the first feature of our idea, that is a Worldhouse construction. So nowadays we can hardly see any conceptual image of a new Martian settlement which is without a dome. Hence, domes serve as an integral part of such a paraterraforming effort. A stable, resilient dome would possibly have all the characteristics which you are able to see on the screen. So first of all, it's a geodesic dome with no internal support. Then it should be fatigue, tension, and deflection resistant. If we want to extend the Worldhouse further, it should have that capability as well. And as the surface pressure of Mars is less than that of the Earth, we also need the dome to be pressurized. And it should be a dome with a thin, flexible, and tensile membrane. Next slide, please. So in this slide, we'll talk more about the kind of materials and the properties that they have, which can be put into use for creating a Worldhouse. So ETFE, ethylene terafluoroethylene, is a fluorine-based plastic which is designed to have high corrosion resistant and strength for wider temperature ranges. So it is basically a lightweight heat-resistant film which is usually used for coating various agricultural and architectural projects such as coverings for greenhouses and protection for solar cells. Also, multi-layer ETFE fabrics with Kevlar fibers can be thermally or chemically welded for ease of integration, maintenance, and repair of the Worldhouse. In an experiment conducted after replicating the Martian environment, it has been found that for the surface, a layer of silica aerogel, which is known to be the best in thermal insulator, if a layer of that is placed over Martian surface 2 to 3 centimeter thick, it could rise the temperature of the surface by around 50 degrees Celsius. So that's something about increasing the temperature of Martian surface. Also, basalt fiber rebar can be a good option for construction of such a Worldhouse. Next slide, please. Okay, for human sustenance inside the Worldhouse, we have environment control and life support system feature included in the Worldhouse. Since it is very difficult to have a controlled climate on a planet like Mars owing to its harsh climatic conditions, we need to create a stable atmosphere which includes oxygen-rich air, ambient temperature, and potable drinking water inside the Worldhouse, which will be covered under this eclipse section. It mainly consists of two parts. First of all is water recovery system, and second would be oxygen generation system, which will target the provision of consistent provision of oxygen. Inside the Worldhouse, with the climatic conditions, it would be monitored using an active feedback control loop. The parameters required would be set initially, but they would change with time depending upon the data from the sensors. The actuators in different subsystems would then act on the feedback to have a controlled climate. So this is something about the eclipse. Can we have the next slide, please? Okay, for the Worldhouse to function properly, as Richal mentioned, we plan to make it autonomous. Hence, there are some power generation and energy storage ideas which can be implemented. First of all, would be a nuclear power system. So on the screen, you are seeing NASA's kilopower fission reactor, which is a part of kilopower reactor using Stirling technology project. It's a 15,000 kg kilopower concept that can produce a lot of power. The reactor is fueled by an alloy of 93% uranium 235 and 7% molybdenum. The core of the reactor, as you can see, is a solid cast alloy surrounded by a layer of beryllium oxide, which prevents neutrons from escaping the core and helps to start or initiate a chain reaction. The rate of reaction is controlled by a single rod of boron carbide, which is a neutron absorber. Once the reaction is initiated, the series of fission products cannot be stopped, but it can surely be controlled using the depth of the control rod insertion, which provides a mechanism to adjust the rate at which uranium fissions, allowing the heat output to match the load. So this will be situated away from the base and a few kilometers underground, and it will be covered by the local Martian regolith. This will be the primary source of power for our idea, and its potential applications include nuclear electric propulsion as well. Next slide, please. So some more options about power generation include radioisotopic thermoelectric generators, which are basically lightweight, compact spacecraft power systems that are really extraordinarily reliable. RTGs provide electric power using heat from the radioactive decay of radioisotopes such as plutonium-238 in the form of plutonium oxide. But taking into consideration the uncertainty in supply of such radioisotopes, which also have a half-life of 87.7 years, it can mostly be applicable for deployment of swarm robots for in-situ resource utilization. Then we have solar power and batteries for storage. So during daytime, the panels will supply abundant amount of energy, which will then be stored in the batteries and provided when there will be no sunlight. So two technologies mainly are ultralight amorphous silicon rollout blanket array technology, mainly used for solar photovoltaic cells, and high efficiency inflexible tracking technology, which is very similar to what has been implemented at International Space Station arrays. And it also has multi-axis tracking to achieve maximum perpendicular solar flux incidence throughout the Martian day. After this, regenerative fuel cells and a concept called in-situ flywheel generation and energy storage system for enhanced power generation can be used. The latter being very efficient in terms that it is going to be manufactured locally, and hence it will enable efficient in-situ resource utilization of the Martian resources. Over to you, Khushi.
Thank you, Aditi. I will be taking over now. So, one of the key features for sustainable development in our plan is in situ resource utilization of Martian resources. The in situ resource utilization is the practice of basically leveraging locally available resources on the planet, which in this case would be Mars. Key resources like carbon dioxide, oxygen, methane, and water will be sourced out from the Martian soil. Liquid water cannot exist on the surface of Mars due to low atmospheric pressure. Therefore, the water ice available in the poles will be directly mined. Martian soil is slightly alkaline, containing elements such as magnesium, phosphorus, sulfur, potassium, and chlorine. Leveraging these Martian resources to manufacture essentials on site drastically reduces the mission cost. The top right image shows Martian resources carried back to the world houses. One of the major in situ technologies will focus on producing oxygen. A good example of this technology will be MOXIE. MOXIE is also known as a mass oxygen in situ resource utilization experiment on board the Perseverance rover, visualized on the bottom right. Following that, liquid methane produced from CO2 will be used to fuel launch vehicles, which would drastically eliminate the net carbon footprint of each flight. Reusable launch vehicles can carry extra payload since carrying additional fuel for the return journey will not be required because the refueling will be taking place on the base. Polar ice caps will be mined to obtain water, and further treatment will be done to obtain potable H2O. Martian rocks can be produced by the process of digging, heating, separation of oxides of elements like silica, magnesium, and aluminium. These minerals sourced from the local regolith will be utilized for building energy storage systems for backup. Moving on to the next feature would be experiments planned inside the world houses. Being a large scale project, there are many parameters which could be varied and experimented. To start with, the first phase of experimentation would be setting up small world houses at different locations on Mars prior to the actual world houses. This is to observe if the Martian location has any effect on any of these ecosystems inside the domes. Once the locators are fixed, world houses will be set up. Each world house would have different types of ecosystem to test which ecosystems flourish the best in the controlled atmosphere. Next, here you can see is an artist concept for a vertical farming facility which will be present inside the ecosystems. Each of these ecosystems will have the unique environment, climate, water circulation patterns, supply of nutrients, and all the crop patterns, all of it will be monitored. This slide visualizes the different variety of ecosystem that these world domes would have. Some may have climate with succulents and plants that require less water, whereas the other world houses may have large evergreen trees with humid climate. Some of the world houses may have big trees replicating forests from our home planet Earth. And a similar ecosystem would also have farming lands growing different varieties of crops or floral farms. In every ecosystem, experiments would be done by the robots autonomously to select the best breeds of flora and use biotechnology in the labs inside these domes to grow better crops, plants, and trees. All kinds of robots, rovers, and drones will be made to communicate with each other to work in swarms. Different strategies would also be applied using machine learning and artificial intelligence so that they take correct decision with human help. One such example will be using machine learning to teach them how to distinguish between the different crop patterns and their diseases so that they can run a diagnostic for damaged crops and come to a solution using artificial intelligence. The database for this machine learning and artificial intelligence will be based upon from experiments conducted in the previous space missions and the experiments simulated here on our planet. These are some of the key features that really focused on the sustainability aspect for our project. Now my teammate Savri will be taking over.
Thank you, Khushi. So I'll be starting off with explaining the different maintenance activities that we'll be conducting as a part of our world house. Now, as mentioned before, we'll be having an autonomous maintenance process. Owing to the harsh conditions of the Martian atmosphere, as well as the different activities that are on board this entire world house, which is the development of the flora and the fauna, as well as the machine life exhaustion of the different subsystems inside this world house, it is essential to conduct maintenance of the different systems that we are using. And this we are doing autonomously by using swarm robotics. Swarm robotics is basically where you use a group of autonomous robots that operate amongst each other and rely on one centralized control, which is the computer that will be giving them all sorts of command on the different activities that have to be performed. Now, in terms of maintenance, the major activities we're looking at are to ensure the development and thriving of the ecosystem within our world house. So the flora and fauna, we have to ensure that there's proper tilling, proper addition of fertilizers, proper water supply, so as to ensure that their development is pristine. Other than that, for maintenance, we look at the maintenance of the subsystems, that is the eclipse power and communication system within our world house. And finally, we also have to look at maintenance of the external and internal structure of the dome itself, because as we know, in a world house, if there's any sort of breach or any sort of structural deformity to the external structure, it can result in a catastrophic failure for our world house. So these are the major maintenance activities that we'll be focusing on. Next slide, please. So in the slide, we basically described an algorithm that is used for inspecting a particular damage that is done to any part of our world house, and then the series of steps that the swarm robots will follow to get to the solution. Now, this algorithm is a very common IoT algorithm, which is called as RTTM, which stands for real-time transient model, which gives you real-life communication values of a problem and its solution as well. So in this algorithm, as you can see, for our swarm robots, we have a combination of drones, robots, and rovers. So now the inspection algorithm itself will consist of various parameters like the degree of damage, the possibility of failure, and the usage period of the machine itself. And using all of these variables, the computer will first find out an optimal solution of the problem. Now, the problem itself is presented by the drones who inspect the site and click pictures to measure the degree of damage or the degree of failure. Once this problem is analyzed by the computer and a possible solution comes out, this solution is then transferred to our swarm, which generally consists of rovers and robots that will then execute that particular solution to their best capability. In this manner, this algorithm is executed so as to ensure that proper maintenance is being done, not just for the inspection and damage of machines, but for other maintenance activities like ensuring proper structural integrity of the external dome, as well as to ensure proper development of the flora and fauna and the entire ecosystem within our world house. Next slide, please. Now talking a little bit about the challenges that we'll be experiencing throughout this project. As a paraterraforming concept, not a whole entire terraforming concept, this project has a disadvantage that it requires a massive amount of construction and maintenance activity. We are all aware of the huge launch costs that are required to carry such a large amount of material from Earth to Mars, as a result of which it is essential for us to complete this project in a very sustainable manner. Sustainability is a point that has been brought up multiple times by my teammates during this project. And the reason for that is it is essential to ensure that all of the things that we are doing are either taken in situ, which is using materials that are available on Mars, so as to ensure minimum launch costs for us. Now, another challenge that we are experiencing would be to the water cycle. So basically, since you're doing a paraterraforming and not a complete terraforming, which is that the entire planet's ecosystem isn't being altered by you, a water cycle is something that will require some thinking into for this particular project. The reason for that is you have a roof in the dome, and the roof isn't tall enough to actually develop clouds and to complete the water cycle by providing rainfall. As a result of which, your water will either be depending on some external source, which is either beneath the Martian surface or at the polar ice caps. So this is something that is not a closed loop system yet, which is the water cycle. Other than this, the challenges are also the structural integrity and design of the external dome, because this is one feature that if it breaches, it will lead to a catastrophic failure of our entire system and the project itself. Next slide, please. Sustainability. So as mentioned in the previous slide of the challenges, sustainability is key for the entire project, and we need to ensure that we're using resources that are available on the Martian surface for a majority of our project. Now, this means we need to look into technologies like additive manufacturing and in-situ resource utilization, as talked about before, so as to ensure that majority of our resources and majority of our systems are working or right in situ, like working right with the resources that are available to us. Another way of doing that is by sourcing the local regolith for energy and radiation shielding. Now, this is something that is already in works for the Artemis 2024 mission, which is where they'll be using the lunar regolith for protection against radiation. And since the atmospheric conditions of the moon and Mars are comparable in terms of the lack of atmosphere available, this is something that can be again substituted to this project. Other than that, as I already mentioned, we need to look into a development of a water cycle and ensure that we have a closed loop system so as to ensure the development and progress of this project. Next slide, please. Finally, looking at the future scope of the things that can further be worked into when it comes to paraterraforming and world houses. So first of all is the introduction of artificial gravity inside the world house. Now, this is essential not just to ensure a complete Earth-like environment on a foreign planet, but it is also with the point of view that humans are going to settle in these world houses at some point in the future, which is why introduction of artificial gravity is essential. Then we'll be looking at IoT applications for communication and efficient ISRU activities, which is essential because ISRU again leads to sustainability, which is the key for our project. Season-specific domes to replicate climatic conditions. Now, this is basically because if you look at the Earth, we have such a diverse climate available at different parts of our planet. And if we want to replicate that kind of ecosystem on Mars, it is essential to have different domes having different specific weather conditions so that that type of flora and fauna can thrive in that particular environment. And finally, implementation of geothermal energy for sustainability. So for sustainability, we are looking into geothermal energy, and currently we do not have enough data or evidence to back up the use of geothermal energy on Mars as a sustainable option for our world house. As a result of which, as the experiments are carried out and as more data is gathered, this is another alternative or option that we can look into to ensure sustainable energy generation and development. Next slide, please.
We have 4 minutes left.
All right, so that brings us to the end of our presentation. So I would like to thank everybody on behalf of our entire team for giving us this opportunity of presenting our project. And our team is now open for any questions from the audience.
Okay, yeah, so I'll read these questions here. So the first one here is the biosphere experiment on Earth showed that exposed ground has absorbed too much of the oxygen from the dome. Will Mars dome suffer the same problem, and how will it be solved?
Okay, so I think I'll take this one. For the Biosphere 2 project in particular, yes, this was one of the biggest technical failures that the Biosphere 2 project experienced, which is they were seeing a shocking decrease in the oxygen amount within their biosphere. However, the biggest reason for that was the use of concrete in their structures. So basically, when you have a concrete sitting for a long period of time, it absorbs a large amount of oxygen. So it wasn't exactly the soil that they were using that was absorbing the large amount of oxygen, but it was the structure, the concrete that they used for their dome that absorbed the majority part of the oxygen. So in case of the world house, we could make those structural choices and decisions to ensure that the materials we're using do not in any way affect the ecosystem or the artificial atmosphere that we're creating inside the world house.
Okay, another question is, how will self-repair of the dome be implemented? Perhaps the sealant sprayer units of the dome rails?
Yeah, that's one aspect that we considered. And the other aspect was since we are making these domes almost autonomous, we'll be deploying, as said, different robots and rovers inside, not just to take care of the ecosystems inside, but also majority of them would also be looking after the maintenance of the dome. So we will be also having UAVs inside, since we'll be having an atmosphere, which will make them able to fly and reach the parts to repair the domes and patch up the leakages or breaches that are inside the dome. With the material, so we are going for silica aerogel, as is the lightest material with enough strength, and it will also allow sunlight inside. So making use of this aerogel, silica aerogel, to patch up, I think that should fix the problem.
Okay. And then another question is, most habitat projects assume covering with regolith, if not underground, because of radiation. How is radiation stopped in this project?
Okay, I'll like to take this one. So we mentioned about the ETFE polymer in the slides, right? So it's basically known for its high strength and stiffness in extreme weather conditions as well. And its different forms can be highly radiation resistant. Also, we wish to run water tubings around the domes before watering the plants to slow down the effect of radiation. So, as Richal mentioned, if we wish to implement it using the silica aerogel technology, these would again allow enough sunlight, but would again slow down the radiation further. So I think that would target the issue.
Okay. And yeah, it's now the top of the hour, so time for the next workshop. But I have one more question I can give here, if you don't mind, and people can go to the next workshop if they want. Okay, so this last question here is, if you're using a dome to make clouds, it's only 1/3 the gravity on Mars compared to the Earth. I wonder what can be the natural cycle of rain on Mars with 1/3 of the gravity?
So, yeah, I mean, it is going to be really complicated given that we have only 1/3 of gravity, and we are, of course, the clouds are going to happen if not by choice. But there, since we are having an active feedback control system, we are going to monitor. I mean, we wish to monitor the climate inside and make sure that there is not too much of a cloud formation, and also control the cycles of rain, as in when the water plants need watering, and also there are few in our future scope we have adding the artificial gravity by running certain centrifuges inside, though not that big. We still wish to apply in some part of dome so that we have the gravity mimicked as that of the earth. So I mean, there are still research is being done, and our team is also trying to find how we can overcome the shortcoming of having the lesser gravity. But maybe we will also find certain crops and ecosystem wherein there is not much of cloud formation, or the water cycles are suited as that of the Martian environment. Yeah.
Okay, cool. Yeah, that's it for the questions. And I wanted to thank all four of you for giving this presentation here.